In this video, we're going to discuss electric field.
You can't see it, it's electric. You gotta feel it, it's electric. Ooh.
That's right, it's electric. Shocking, I know. Roll the intro.
Do you feel the vibes?
For field forces like the gravitational force or the electric force, we can create a field that is dependent on only one of the objects in the system. For the gravitational force, this is the acceleration due to gravity. That's because since the force relies on two masses, when we divide out by one of those masses, we end up with simply an acceleration. The electric force is a little different. Since it's not based on mass, Newton's second law will not allow us to cancel out an m and give us an acceleration. In this case, we have that the electric force is equal to a single charge times the electric field. In this case, the electric field is effectively a measure of how powerful an electric force will be for any charged object placed in that field. This allows us to characterize the behavior of a system without actually putting any particles inside, and therefore allows us to predict the way a particle will act once it enters the field.
Attracting forces come and go, man.
That's why we need something to characterize our system rather than the individual particles. We use what's called a positive test charge to figure out the equation for the electric field. This test charge has a charge of +1. That means that the electric field will characterize what happens for any positive charge that's put in the field at the amount that will be scaled by the amount of charge that's placed in the field. Negative charges will just have the opposite effect. So if a field would push something to the right, a negative charge would be pushed to the left. This means that positive charges will have an electric field that radiates outward, since they would repel any other positive charge in the field. And negative charges will create an electric field facing inward radially, because they would attract any positive charge placed in their field. Since we know that the electric force is simply the constant k times the two charges divided by the radius between them squared, when we get rid of one of the q's, we are just left with that the electric field is equal to k times the characterizing charge divided by the radial distance of that charge squared. So much like acceleration due to gravity changing based on how far away from a planet you are, the magnitude of the electric field, and therefore the magnitude of the electric force, will change based on how far you are from the central object. Keep in mind that the electric field is characterized by all electric force on the object. This means that if you have a system of multiple particles, you will have an electric field that's based on all the particles within that system. And then a charged particle will move along those electric field lines when placed in that system. When defining our system, we often decide that all the charges are static. This means that they don't move in relation to each other. So the electric field that we calculate will be stable, and the charges won't move toward each other or away from each other. The only particle that moves would be a particle placed in the system and in the electric field. When you have opposite charges, the electric field will go from the positive charge to the negative charge. But note that it's only a straight line in the middle between the two. When you have two particles of the same charge, they will obviously repel against one another, or attract against one another. This means that the electric field will be 0 at the mid spot between them. That's because the two electric fields will perfectly cancel each other out. We can expand upon this for systems with more than two charges. And likewise, we don't need each charge to have the same magnitude. This can change our electric field considerably and give us some pretty interesting things. If we expand this into a calculus form, we can have continuous distributions of charge, but that's a subject for another video. And that wraps up our video on electric fields. So I know this one was a lot of exposition and setting up for future things, but electric field is something that we're going to focus on quite a lot in this unit especially. It will become important later on when we talk about magnetism as well, so it's an important topic of conversation. Anyway, thanks for sticking around, and I'll hopefully see you in the next one. Don't forget to like, comment, subscribe for more physics in the future. Appreciate it.